Hello everybody, we continue our lectures, and today is lecture 13, Friday 13, so very 13. And okay, so section 13.1, limit theorems. Here we'll consider several properties of the limit for functions, which are quite similar to the corresponding properties of the limits for the case of sequences. So they are completely analogous. But of course, we should write down necessary conditions. So let fg from D to R point P be limit point for D. And also we suppose also limit as x tends to a f of x equals to, let's say, L1, limit x tends to a g of x equals to L2, suppose that for a positive number delta for any x in B P delta without P intersected with D, we have the inequality f of x less or equal g of x holds. Then L1 less or equal L2. So proof is very easy. We refer to the corresponding properties of the limit of sequences. So we use Heine definition. So take arbitrary sequence xn in D, xn not equals to a, and p not equals to p, or p, everywhere should be p. We have always p, everywhere should be p. Xn not equals to p, and limit of the sequence xn equals to p. So we take arbitrary, sometimes such sequences are called Heine sequences. Then, by definition of the limit of sequences, for arbitrary delta, in particular for our delta, for delta, just this one, delta, for the number, let me write, for the number delta, just that one, for the number delta, we can choose or find, we can find, doesn't matter, we can find natural n such that for all n greater than n, we have xn minus p less than delta. Also, it is greater than 0 because of this condition, xn doesn't equal to z and doesn't equal to p, right? Okay. So, hence, for all members of the sequence xn, n starts from capital N plus 1 up to infinity, the inequality f of xn less or equal than g of xn holds. Why? Because of this. Look, what means that inequality? Together with xn is in D, right? So it means that all members of our sequence, I mean for indices greater than capital N, are situated in that set, the intersection of D with the neighborhood without P, because this neighborhood without P is just that set, and the set which is defined by such inequality. Hence, by the supposition of our theorem, we have this inequality. Okay, then look what happens. Now, by the definition, by the Heine definition, we have limit f of xn equals to L1, since xn tends to p, so f of xn tends to L1, and limit g of xn equals to L2. And hence, by the property Okay, of course I don't remember precisely what is number of this property, so if all members of those two convergent sequences satisfy that inequality, then same inequality is valid for their limits by the property limits of sequence, limits of sequences and inequalities. We have couple of theorems there, and hence we have L1 less or equal L2, and that's all. That is the first theorem. Okay. Second theorem is a converse assertion, Theorem 2. And the same first sentence is completely the same. So let Fg from D to R, P be a limit point of D, and we have the following limits: f of x equals to L1, limit g of x equals to L2, and now we suppose only inequality L1 less than L2. Then there exists delta positive such that for all x in same set dp delta without p intersected with d, the inequality f of x less than g of x holds. So you see, this is a converse assertion. Here we supposed the inequality between functions, and we deduce the inequality for limits. And the second assertion is in some sense converse. So we have an inequality for limits, then we deduce inequality for the values of the function, of the functions. And let me emphasize once again, here we preserve non-strict inequalities, and we can deduce only from the strict inequality something. So if you suppose here non-strict, then nothing can be said about the values. So proof. Proof. By contradiction. By contradiction. But what is contrary here? So, we want to prove that there exists something such that something is valid. And what is contrary? For arbitrary. For arbitrary delta positive, there exists X in this set punctured neighborhood intersected with D such that the opposite inequality is true, so f of x greater or equal than g of x. Now we use similar consideration to what we used many times, in fact. So here it is written for arbitrary positive delta, right? So we suppose that delta is taken smaller and smaller. So we start from, let's say, delta equals to 1, then we choose delta equals to 1/2, and so on. So delta 1 over n, and so on. So such an infinite chain of values of delta is chosen. And for each choice, we can find x, and this x will enumerate using denominator. So x1 in b of p1 minus p intersected with d. Here there exists x2, b, p 1 over 2, and so on. There exists xn, b, p 1 over n minus p intersected with d, and so on. And each of those x's satisfies the inequality, so I write all those inequalities here. Okay. Now, what can we say about the sequence? So we have constructed a sequence. What can we say about that sequence? Look, what means this relation? This neighborhood means that we have the following inequality. Yeah, first of all of them are in D, right? In D. And also we have inequality xn minus p in modulus greater than 0 because of punctured neighborhood, less than 1 over n. Now, look at this inequality. Both left and right hand sides tend to 0 as n tends to infinity. The left hand side is a constant sequence, the right hand side we considered 1 over n tends to 0. Hence, by the two policemen Policeman theorem. The middle part also tends to 0. So, what we have? Let me write then. We have a sequence in D. All xn do not coincide with P, and the limit of the sequence xn equals to P. Then, by Heine definition, what we conclude? We can conclude that the limit of f of xn equals to L1, and the limit of g of xn equals to L2. That is what we deduce from the Heine definition. So, both limits we have, right? And also we have such an inequality for row n. Hence, by those two, what we can deduce, again from limits of sequences and inequalities, in fact, the same theorem which was used in the first part. We deduce that similar inequality is valid for the limits. So L1 greater or equal than L2. But that is a contradiction. That is a contradiction. So contradiction. And that's all. So we have proved. Okay, no questions. At least if there were, they are raised. Now, wait a minute. Okay, no examples yet. Okay. Now, we consider arithmetical properties of the limit. Arithmetical properties. And we need formal definition of arithmetic operations with functions. Of course, it's quite trivial, but let it be. So, definition. If f g from D to R, then f plus minus g from D to R is defined for all x in D as so f plus minus g of x equals to, by definition, what is it? It means we add or subtract correspondingly the values of the function. And analogously, f times g of x is f of x times g of x, and f over g of x is f of x over g of x, of course, for g of x not equal to 0, right? Otherwise, we cannot define this operation. Okay. So it means that the last function is defined, so f over g is well defined from another set, d tilde to r, where d tilde is the set of all x in D such that g of x not equal to 0. So the ratio is defined not everywhere. Okay, now Theorem 3. Theorem 3. Let f g from D to R P be a limit point of D, limit as x tends to P f of x equals to L1, limit as x tends to P g of x equals to L2, then first limit of the sum or difference is equal to the sum or respectively difference. The limit of the product times g of x equals to L1 times L2, and third, for L2 not equals to 0, the limit as x tends to P f over g of x equals to L1 over L2. Proof. Consider arbitrary. Consider arbitrary sequence xn, Heine sequence in fact. So xn not in D, xn not equals to P, and the limit of xn equals to P. Then, by the Heine definition, what we have? We have that the limits of the sequences f of xn is L1, and the limit g of xn is L2. Then by the limit theorem for sequences, arithmetic operations, what we have? We have that the limit f of xn plus minus g of xn is L1 plus minus L2, and the limit f of xn times g of xn is L1 times L2. And since the sequence xn is arbitrary sequence, which satisfies properties from the gain definition, then it follows first and second properties, assertions of the theorem. So first and second are proved. Now for the third. For the third, we have limit x tends to p g of x equals to L2, L2 not equals to 0. Doesn't matter, let's say L2 greater than 0. Then, look, we can use Theorem 2. So, as f of x, we consider just zeros. So, by Theorem 2, what we can deduce? There exists delta greater than 0, such that for all x in B of P delta without P intersected with D, we have similar inequality, so g of x is greater than 0. So it means g of x, I'll write here, g of x is not 0. Here it will be greater, and for L2 smaller than 0, g of x is smaller than 0. So in any case, we have this inequality, g of x is never 0 for all x from a neighborhood, punctured neighborhood of P. Then, from the property limit xn equals to P, we deduce that there exists n natural such that for all n greater than n, all members of our sequence xn belong to this set B of P delta without P intersected with D. Of course, here we should use also both suppositions from the beginning, right? And what it means? It means that g of xn is not 0 for all sufficiently large n. Hence, we have that for the sequence from d tilde xn not equals to P limit as n tends to infinity of xn equals to P, where d tilde is, what is d tilde? D tilde is here. This is the set of all x in D, g of x not equals to 0. So if we suppose that xn is in d tilde, and in fact arbitrary sequence from D satisfies this supposition for sufficiently large indices n. Then what we have? Then we have that the limit as n tends to infinity f over g of xn. Okay, I may write like that. Now everything is defined, and again by same arithmetic operation property L1 over L2. And that is what we wanted to prove. The last part is proved. So, okay, example. Example 1, for this section. So consider f from r minus 7 to r, so given by my f of x equals to okay, x squared plus 2x minus 3 over x plus 7. So, and I forget to write which limit we are interested in. The limit as x tends to minus 2 f of x. So, minus 2 is the limit point of that set. Hence, we can write, so limit as x tends to minus 2 of x times limit x tends to minus 2 of x squared plus limit x tends to minus 2 of 2 times limit x tends to minus 2 of x minus limit x tends to minus 2 of 3 divided by limit x tends to minus 2 of x plus limit x tends to minus 2 of 7. Limits of constants, of course, are same constants, hence, and limit as x tends to p of x equals to p. So we have minus 2 times minus 2 plus 2 times minus 2 minus 3 over minus 2 plus 7, and that is 4 minus 4 minus 3 over 5. Okay. Example 2, I don't see any reason. Okay, let's have a break. Continue. The next section, not section, sorry, one more example, quite important example. In fact, I considered similar example just after definition, but now it is even better. So, example 2, limit is x tends to -1, x squared plus 6x plus 5 over x plus 1. Here once again we have a function with the domain d is r minus -1, and -1 is a limit point of this set, it's for sure. Now, we cannot substitute as we did before. Why? Because in denominator we have 0, and hence we cannot use this theorem because of the supposition that the limit of the denominator is not 0. Then how we proceed? We proceed as follows. So I did it at the beginning of the chapter. Now once again same idea is used, right? And now look, on this set D, everywhere except for -1, our function is equal to x plus 5. And after that, we can substitute. So once again, this is typical example which explains why we need those huge definitions with epsilon, delta, and so on. Because look what we do. Firstly, we cancel multiply x plus 1. What can be done since x doesn't equal to -1? X doesn't equal to -1. And after that, we substitute x equals to -1. That is logically very strange, but this is not strange because of all theorems and so on, because now everything was proved here, right? We can cancel because it will be the same function on this set after cancelling. So those two functions, they coincide everywhere on D. Hence their limits are the same. Okay, so next section. Next section, 13.2, Cauchy's criterion. Cauchy's criterion. So, theorem. Theorem 1 for that section. Let f be from D to R, P be a limit point of D. Then there exists a finite limit as x tends to p f of x if and only if for arbitrary epsilon greater than 0 there exists delta greater than 0 such that for all x in D, maybe let me write x1 and x2, maybe x and t in D, 0 less both x t d intersect to, let me write it by, not by inequalities, b of p delta minus p, like that. Let me write it like that. And for all those x and t, we have f of x minus f of t less than epsilon. So, if you compare it with the Cauchy definition, in Cauchy definition we had inequality f of x minus the limit smaller than epsilon. Here we compare, so in the definition we wanted to have values of the function as close to the limit as we want. And Cauchy criterion says that for the existence of the limit, it is necessary and sufficient that the values of the function are close to each other when we approach to the value p. So in inequalities, oh, maybe I forget to close bracket. Yeah, close bracket. In inequalities, yeah, we can another version, same chain of quantifiers can be rewritten as follows. For arbitrary epsilon, there exists delta, such that for all x in D, 0 less x minus p less than delta, and for all t in D, 0 less t minus p less than delta, we have f of x minus f of t less than epsilon. That is same criterion written in, the same chain where we wrote explicitly these boundaries, these neighborhoods. Okay, so proof. Let's start with necessity part. Necessity. So, here we suppose there exists a limit. So let it be L equals to the limit. Tends to be f of x. And it means by Cauchy definition, for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x in D 0 less x minus p less than delta, we have an equality f of x minus L less than epsilon. Now, look. In fact, instead of epsilon, I can choose here epsilon over 2, because this is also a positive number, arbitrary positive number. So, it means that same thing I can say for every t in D, 0 less t minus p less than delta. We have also similar inequality, because it doesn't matter which letter we use. We have a property that for all values t or x which satisfy that inequality, we have this inequality for the values of the function. Now, for the same chain of quantifiers, what can we write for the difference f of x minus f of t? I can subtract and add same L. And then, by the triangle inequality, we have f of x minus L plus f of t minus L. I can change the order because of modulus. Now for both terms we have inequality less than epsilon over 2, hence lastly we have epsilon. So what is underlined is precisely what we wanted to prove. So necessity is ready. Now sufficiency. Sufficiency part. Now we have that inequality, right? Take arbitrary sequence xn, and from 1 to infinity in D, xn not equals to p, and the limit of xn equals to p. Then, for arbitrary epsilon, there exists delta such that the whole chain is satisfied. I I'll write it here. For all t in D with the same inequalities, we have f of x minus f of t less than epsilon. Okay, now from the definition of the limit, by the definition, what we deduce? For arbitrary positive number, and I'll take here just that one, delta, which we can choose from arbitrary epsilon. For that delta, there exists natural n such that for all n greater than this capital N, we have inequality xn minus p less than delta. Moreover, it satisfies also greater than 0 because of that supposition, and of course all xn are in D, right? Hence, we can, same inequality is true for arbitrary m greater than n, right? Also, right? Under the same supposition about capital N. So it means that we can take here in the Cauchy criterion, instead of, let's say, x, xn, and t, xm. So what we deduce then? Let me write. So, for arbitrary epsilon greater than 0, we have chosen delta, and from the delta we found capital N, so I'll write the final step. We find capital N such that for all n smaller than capital N, and for all m, greater, for all n greater than capital N, for all m greater than capital N, what we have? We have f of x n minus f of x m less than epsilon. So, once again, I substitute instead of x, xn, instead of t, xm. But this is precisely the definition of Cauchy sequence. So it means that the sequence f of xn is a Cauchy sequence. Hence, we have proved in the section about Cauchy sequences, f of xn converges. Let it be limit f of xn equals to L. Did we finish the proof? Look, what we have proved up to now. So we took arbitrary sequence, xn and dxn not equals to p, limit of xn equals to p, and we have proved that that sequence converges. We didn't prove the result yet. Why? Because in principle, I wrote here capital L, but for another sequence, we can find in principle another limit, right? So suppose now there are two sequences x and 1 in D, x and 1 not equals to p, and the limit x and 1 equals to p, and x and 2 in D, x and 2 not equals to p, and the limit of x and 2 equals to p, such that limit f of x and 1 is a 1, and limit f of x and 2 is L2, and L1 not equals to L2. So, to finish the proof, what we should have? We should prove that there exists a finite limit, right? And according to Heine definition, what means there exists finite limit? It means for arbitrary sequence, the limit of the values is the same for both sequences. Because now we know precisely that there exists a limit, for sure, for arbitrary such sequence. But we cannot guarantee yet that for two different sequences we have the same limit. So suppose that we have different limits. Consider such a sequence. X 1 1 1 2 2 1 2 2 3 1 3 2 and so on. So we mix them, we alternate the choice. So firstly we choose member of the first sequence, then second, then again first, then second, and so on. Alternate the choice between two sequences, right? Then what can we say about that sequence? This is a new sequence, and what can we say about this? Look, all of them not equals to p, all of them are in D, and the limit of that sequence is p, right? So this sequence converges to p. Hence, by the proven part, there exists limit of the values f of x, okay, let it be yn or tn, but tn and from 1 to infinity, f of tn exists, right? So we have proved that once we have a sequence which satisfies those suppositions, all members are in D, all of them do not equal to p, and the limit of that sequence equals to p. Once we have such a sequence, the sequence of values converges. So now we have a sequence which satisfies all those suppositions, Tn, just alternate xn1, xn2. And by the proven part, there exists a limit, f of Tn. But now what? Look carefully at the sequence f of Tn. What is it? The sequence f of Tn is as follows. What is this f of Tn? F of Tn. Let me write it in more details. That is f of xn 1, 1, then f of x1, 2, then f of x2, 1, f of x2, 2, and so on. So, the sequence f of Tn, they have two subsequences. F of x and 1 and f of x and 2 are subsequences of f of Tn. Why? Because f of x and 1, these are members with odd indices from here, right? F of x and 2 are members with even numbers. And they have different limits. They have different limits. Hence, f of Tn has two different partial limits. L1 not equals to L2. But if a sequence have two partial limits, different partial limits, then it cannot be convergent. Right? So, look, we supposed there exists a limit. Just now, we got a contradiction. And that is a contradiction. And it means that the proof is over. Okay, so yeah. Okay, maybe maybe some remarks about the Cauchy criterion. And we considered infinite limits, right? Remark. For the infinite limit, limits the Cauchy criterion is not satisfied. So, but of course, what means infinite limit? In principle, let me write what means infinite limit. Infinite limit of a function. What is infinite limit of a function? let me recall. In fact, for example, if f from D to R, P is a limit point of D, then what means limit as x tends to P f of x equals to plus infinity? What it means, plus infinity, right? Or plus, we may omit plus. What it means? By Heine definition, it's quite natural. What by Heine definition? Heine. For arbitrary sequence xn in D, xn not equals to P, right? And limit of xn equals to P, we have limit f of xn equals to plus infinity. And of course, we can write plus or minus infinity, right? So similar for minus infinity, right? Doesn't matter. And so Heine definition is clear. What is for Cauchy definition for the infinite limit? Cauchy definition for infinite limit. That is, for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x in D 0 less x minus p less than delta, we have f of x greater than, 1 over epsilon, just to underline the fact that epsilon is large, but of course you can write epsilon, doesn't matter. That is for limit plus infinity and f of x less minus 1 over epsilon for limit minus infinity, right? That is for infinite limits. So for the infinite limits, Cauchy criterion is not satisfied. But for finite limits at infinity, we can also consider limits at infinity. It is valid. So this was remark 1. Remark 2. Cauchy's criterion is valid for finite limits at plus or minus infinity. How it looks like? So, of course, infinity is a limit point of D, so let's say let f be from a plus infinity to R, there exists a finite limit as x tends to plus infinity f of x, if and only if for arbitrary epsilon greater than 0 there exists delta greater than 0, such that for all x and t in, how it was written, in b of plus infinity delta intersected with a plus infinity, the inequality f of x minus f of t less than epsilon holds. And analogously for minus infinity, right? Just replace here minus infinity and converse order of this. And what means this limit? So definition of that infinite limit. Okay, Heine limit is clear, right? So for arbitrary xn greater than a limit of xn equals to plus infinity, there exists a limit f of xn equals to L. So this is L, right? That is L. This is equals to L. And Heine and Cauchy, this is Heine and Cauchy will be for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x greater than a and x greater than 1 over delta, we have f of x minus L less than epsilon. That is Cauchy. Analogously, we can define limits at minus infinity. So let's say limit x tends to minus infinity f of x equals to L. Cauchy will be for arbitrary epsilon. There exists delta such that for all x less than a less than minus 1 over delta, we have f of x minus L less than epsilon, right? That is. And once again, Cauchy's criterion is valid for finite limits as plus or minus infinities. But this is not true again for infinite, and we can also have arbitrary combination of infinities, and for infinite limits Cauchy's criterion is not true. Okay, that's all for today.